So now we're going to look at a required practical, and it's the separation of species by thin layer chromatography. So we're going to look at the analysis of the composition of some common medicines. So we're going to be looking at aspirin, paracetamol, caffeine, and anodine extra. So the method comes in 3 parts, and the first part is preparing the samples. So what we do is we crush an aspirin tablet with a pestle and mortar to begin. So we're first starting off with aspirin. And then we use a balance, which are just scales, and a weighing boat to weigh out 0.1 grams of this aspirin. We then transfer all the powder into a bottle, and we add 0.5 centimeters cubed of ethanol. And then we repeat these 3 steps for the paracetamol, caffeine, and anodine extra tablets. So what this does is just turns it into a liquid. And then for part 2, we actually run the chromatogram. So the first step is to use a pencil to draw a line 1 centimeter above the bottom of the plate and mark 4 equally spaced dots onto this line. One thing to note is that you should avoid touching the surface of the plate with your fingers, as this will contaminate the plate. So we draw a line 1 centimeter above. And this is because we want the solvent to be below this pencil line to start off. And so we actually just get the evaporated solvent, which is going up the plate and not just the liquid. And then we label each spot with the first 3 letters of each tablet. So this will make it easier at the end for us to know which one is which. So for example, we would have ASP for aspirin. And then we use a capillary tube to apply a tiny drop of each of the solutions onto their corresponding pencil dots and allow the plate to air dry. So a capillary tube is basically just like a pipette, but a lot smaller. And so what you do is you keep your finger pressed at the top, and then you suck some of the liquid in, so some of your sample. And then when you release your finger, the pressure will be released, and so put a tiny drop of this liquid onto your pencil spot. And so that's how we put all of the liquids onto their corresponding spots. And then we allow the plate to air dry. We then add approximately 100 centimeters cubed of ethyl acetate, which is going to be our solvent, to an 150 centimeters cubed beaker. So we would do this using probably a measuring cylinder. And then we place the TLC plate into the beaker and make sure the solvent is below this pencil line drawn on the plate. We then place the lid of a Petri dish, so just a round lid, onto the beaker, making sure that it's a tight seal, and so the solvent vapor inside is saturated. And saturated just means that the solvent vapor is very concentrated inside this beaker. And when the level of solvent has reached about 1 centimeter from the top of the plate, we then remove it and mark the solvent front, so where the solvents ended up, with a pencil, and dry the plate in a fume cupboard. And then the last part is the analysis. So the first step we do is place the plate under a UV lamp to visualize the spots, because all of these spots will be invisible. And so we either need to use UV light or ninhydrin sprayed onto the spots to make them visible. We then draw crosses at the center of each spot. And then we measure the distances to these centers of the spots from the initial line, or sometimes called the origin, and also the distance to the solvent front from the initial line. And then we calculate the RF values. So that would be using the equation RF equals distance traveled by the spot divided by distance traveled by the solvent. So on the diagrams, on the first one on the right, that's what it would look like when we have the plate inside the beaker. So we have the lid at the top. And then here we have the beaker. And then this liquid here is our ethyl acetate. And as you can see, it's below this initial line here. So this line here is the initial line. or it's sometimes called the origin. And so we have these spots which are going up. And we wouldn't actually exactly have this because we would have 4 spots. So on the initial line, we would have 1, 2, 3, 4 like that, evenly spaced. And so we would have dots going up the paper from these 4 spaces. And they also wouldn't be coloured because our spots will be colourless. And so after we've run the chromatogram, the bottom diagram is what we'll have, what our TLC plate will kind of look like. But our one won't look exactly like that, because again, we started off with 4 pencil spots. So these pencil spots will still be here. So we have 4 like this. And then on our chromatogram, we'll have colour spots, but under UV light, we'll be able to see some visible spots. So for example, if we had this one as aspirin, we might have aspirin up here. And if we had this one as caffeine, for example, it could be maybe down here. And so we actually wouldn't have these kinds of spots because we're not doing it all. We're not just separating one thing out into components. And so what we would do is that here we have our solvent front. So that's how far the solvent has moved, and this should be about 1 centimetre from the top. And so what we do is we measure the distance from this solvent front to the initial line. So this is distance moved by the solvent. So this will always be the bottom of the fraction to work out the RF value. And then, for example, for aspirin, what we would do would be you'd mark a cross at the center of the spot, and then you would work out what this distance is here from the central part of the spot to the initial line. And so this is the distance moved by aspirin. And then you would just calculate the RF values of all of these. And so what you should find actually at the end of this experiment is that anodine extra will have 3 different spots. So if we had an anodine, so if I draw the TLC plate out again, and we have the solvent front here, and if we have the initial line here and we had anodine, then what we would get would actually be 3 spots. So we'd have one here, and one higher up. And what this actually tells us is that it actually has 3 different things in this anodine extra. And if you compared it to the aspirin, the caffeine, and paracetamol, so for example, aspirin might be here, and then we would have paracetamol. So you can see it more easily, but they would be invisible. And then you could have the caffeine here. And so what we can conclude about anodine extra is that it actually consists of aspirin, paracetamol, and caffeine, because all of these components have RF values. All of these 3 components have RF values which are the same as aspirin, paracetamol, and caffeine. So that's what you should find with this experiment.